who is coming to us here at, oh, everyone please consent to being recorded. It's mostly Evan who needs to do that. But anyway, Evan's coming to us from Madison, Wisconsin, a place near and dear to my heart as well. And I am both Evan's academic and research advisor here at Lawrence. So I met Evan among his first days on campus, and I feel like I kind of knew who he was from the get-go. He's a very even-keeled guy, and expressed his interest in math, physics, and chemistry from the beginning. And it's been fun to get to have conversations with him, periodically, seeing where his studies have taken him. And I was gratified that he stuck with chemistry and indeed joined my research group. Was that 2 years ago now? It feels like forever ago. So he's going to tell us a story today about some research that he really picked up on his own after working in my research group for a summer. And I think it is a nice description and hopefully a great future direction for my research lab. So less of me, more of Evan. Evan, the floor is yours.
All right. Before we get started, I just want to let you know, if you want to see my face during this presentation, a good spot to put me is in the Put Me Here box. You don't have to look at my face if you don't want to, but if you do put me there, you won't be blocking any of the content on the slides. So thank you all for coming to my senior experience talk. I had a lot of fun working on this project, and I hope you're able to pull something interesting from this talk to be able to bring home with you. So today I'm going to be talking to you about taking a molecular census of a nanoscale apartment complex. And obviously there's going to be some chemistry behind that metaphor, so we're going to jump right in. Here we go. One goal in recent history that scientists have had is trying to employ molecular scale control using macro scale materials. And what I mean by that is we have some macro scale material, meaning like a crystal or a powder, something that we can interact with physically. But we also have very good molecular scale synthetic control over that powder's attributes, or over that material's attributes, to employ it to do particular things on the molecular scale. An example of this might be something like a graphene sheet. A graphene sheet is made up of interlinking carbon atoms, making up these cool hexagons. And one important thing about graphene sheets that is applicable to most of these molecular scale materials is that we're looking for a material that has some type of repeating unit. That means that if we can make a synthetic change to a particular single unit, that synthetic change will hopefully be able to just propagate across the entire molecular structure, which is really, really nice. So in the case of a graphene sheet, we're looking at a two-dimensional material here. It is one atom thick, and then it spans out in the two other dimensions, two other directions. Another like this might be something like a metal organic framework. Metal organic frameworks are actually important to my talk, so I'll be diving in more in depth on what these are. But one important thing to note about these metal organic frameworks is that while they can go in both, or they can be both two-dimensional, they can also be three-dimensional, like this box you see right here, propagating out in 3 different directions. So a metal organic framework, or MOF, is a continuously linked framework made of these metal centers or metal clusters and organic linker molecules. So as you can see in this example, we have our metals, we have our organic linkers, and they're actually able to self-assemble under particular conditions to make a metal organic framework. Now, self-assembly is really nice. A lot of times this means that we're only looking at a single-step synthesis, which is really, really a huge benefit. And as you'll notice with this metal organic framework, we see that this is a three-dimensional framework where we have the framework propagating out in three dimensions, giving us these box-like structures. Now, one really useful thing about three-dimensional metal organic frameworks in particular is that they're porous. So as we can see, they're made up of hollow boxes, and there's no walls on the boxes either. That means that guest molecules can actually be included inside of the structure. And the inclusion inside of the structure can be really, really nice. It can either change the function of the framework, or it can change the function of the molecule, and we can use this for many, many different things. For example, there are a bunch of different things that MOFs have been used for. I'm just going to go ahead and give you a couple. One big example that people are really interested in is using MOFs for gas capture. So as you can see from this example, we have carbon dioxide gas and hydrogen gas mixed together. Carbon dioxide gas is more selectively incorporated into the pores of the metal organic framework, and this allows us to separate the two gases. And this might be useful for something on an industrial scale. Perhaps we need to separate these gases for some industrial purpose. But this type of gas separation can also be used for a lot of other interesting things. For example, if we think about the current climate crisis, carbon sequestration is a big thing that we might be interested in doing, trying to get carbon out of the atmosphere. And one way to do this would be to maybe try to synthesize a MOF that we can use to selectively incorporate carbon dioxide out of air, as opposed to out of hydrogen gas in this case. Another use for MOFs is in catalysis. So for one, MOFs can be used as catalysts, where reactants are able to enter inside the pores of the MOF and react within. And this is kind of akin to some type of synthesized or synthetic version of, say, a protein. We know that proteins have particular active sites that are very much prepared specifically for distinct molecules to be able to react them there. The same way that this MOF might work. We might have a very particular synthetic setup that wants to incorporate specific reactants for, again, a specific purpose. These MOFs can also be used in catalysis by incorporating already existing catalysts as guests inside of the framework. So frameworks can actually be assembled around catalysts, or catalysts can be included within these frameworks and it actually will change the property of the catalyst, again, giving us some interesting tunability. On another note of tunability, we also have conductive tunability. For example, this metal organic framework, depending on what you dope the framework with and how much you dope the framework with, you see different types of conductivity, you see different resistance pathways throughout the metal organic framework. So this type of tunable conductivity is also really, really interesting. So the big thing is with these MOFs, we can make small synthetic changes and might be able to make that makes them very, very tunable. So while we have all of these very interesting things that we know we can do with MOFs, not much is actually known quantitatively about the solution phase dynamics of molecules in these MOFs. And so what I mean by that is, well, we might know that, okay, if we have a larger pore size on a MOF, we'll be more likely to be able to include a larger molecule. That makes sense. But we don't necessarily know how a larger pore size will relate to quantitative like uptake times, or the number of molecules included, just if we are working with a single molecule or a particular molecule. So maybe making the pore bigger, well, of course, would be able to incorporate more molecules into the framework, but maybe it'll also allow more molecules to leave the framework. So we don't really have a great idea of what's going on there. We might also be interested in, what does the actual time versus uptake curve look like for these frameworks? We might be wondering, is it something kind of logarithmic like you see here? Maybe it's more of a linear relationship. We kind of are interested in what that relationship looks like. And beyond just what that relationship looks like, we also want to know things about the equilibrium. Obviously, we want to be able to have particular equilibrium conditions to say if we want to uptake a particular thing into the framework over the surrounding other molecules in the system. And we want to be able to see, okay, is the concentration of the guest molecule higher in the framework than in the outside solution, lower in the framework than in the outside solution, and other things like that. We might also be interested in solvent effects inside of the framework. If we look at how you synthesize these metal organic frameworks, they're almost always done in the solution state, and we end up with a framework that has a particular solvent in the pores. And depending on what solvents in the pores, this can actually influence how easily guests are taken up into the framework, either on a timescale level or maybe even on an equilibrium level, depending on what the solvent is and what the guest is. So with all of these big questions in mind, the goal of my project is really to begin to think about these questions and kind of try to devise a method that we could use to probe some of these questions, not to necessarily answer a specific, very focused question. So the goal is more of a method development, and I'm going to quickly run you through kind of the different steps of my project. So to start off, it would be looking to synthesize a metal organic framework. In this case, we're not going to be looking for a particularly unique or novel framework to be working with. We're more going to be looking for a framework that we already have some idea of what's going on, hopefully one that's well documented so that we're able to know when we synthesize it, and we're not going to have to do too much work characterizing it. From here, we could move to put the metal organic framework into a solution with EPR active molecules. Now, EPR stands for electron paramagnetic resonance, and I'm going to get more in depth on what EPR is a little bit later. But for now, just know that these EPR active molecules are active to the instrument, EPR, and that's very, very important because once these molecules have been incorporated into the framework, we can actually begin to use EPR to selectively look at these molecules, ignoring the rest of the framework. And the great thing about EPR is that it can be used quantitatively. So in this case, we would be looking to actually count the number of molecules that have been incorporated into the framework after a given amount of time. And that would be really, really useful for answering some of these questions we want to be looking at. So I can kind of akin this project to opening an apartment complex, hopefully a fun metaphor. We can start off by building our apartments. We can go ahead and synthesize a MOF that we're interested in, that we think might be a good candidate for the task at hand. Then we can check the specs, make sure all the windows and doors are in the right places. We can go ahead and use some different techniques to hopefully confirm that we've developed the framework that we hope to prepare it for future projects. From here, we can open our apartment, start to let those people in. In this case, this would be soaking our framework in a solution with our EPR active molecules. And then from there, we can take our census after a known period. So we're going to be looking to use the instrument EPR to be able to, after certain amounts of time, look at the molecules inside of the framework. So we can start with building our apartments, or in this case, synthesizing the framework. So the framework that I chose for this project is called MOF5. And MOF5 has been around for quite a while. It was first synthesized in 1999, which is pretty early in comparison to the big MOF boom that has been happening more recently. And the reason I chose MOF5 is one, because it's quite well documented. And its synthesis is not particularly complex. I also chose this framework because it has very good stability in a number of different solvents. And that would be important provided I could make it to a phase where I want to be looking at different solvent effects inside of a framework. And the pore properties for this framework should also be good. It is a cubic framework, so hopefully all of the pores would be the same size, which makes it a little bit easier to think about the molecules moving throughout the framework. And also the pores are large enough to incorporate some of the EPR active molecules that I'm interested in. So you can see the framework down here. You can see that it's made up of oxygen, carbon, zinc, and hydrogen. In this case, we're looking at a system with metal clusters, not just metals. So we have 4 zinc metal atoms. They're actually at the center of those blue tetrahedra, and they are bonded to the oxygen in the center, and that makes up our metal cluster. And then for our organic linker molecules, we're looking at that benzene ring with the 2 para-carboxylic acids that have been deprotonated and then chelated to our metal centers. So how did I actually go about making this MOF5? Well, starting off, an important thing to note is that all of the synthesis was done in dimethylformamide, or DMF. And this is important to note because all of the spectra that I'll be showing you later is of MOF5 that has some amount of DMF in the pores already, because as I said, when you synthesize a framework, you're likely going to end up getting the solvent. You're always going to end up getting the solvent in the pores. So I made a solution of DMF and terephthalic acid, which is that linker molecule that I was talking about, as well as triethylamine. And the triethylamine was there to deprotonate the acid and prepare it for chelation to our zinc. So in this case, you want to add the zinc as a solution as well. So I slowly added a solution of zinc in DMF. And depending on how quickly you add the zinc, it can actually have effects on the size of your crystals that you grow. So I was not necessarily super worried about the size of the crystals that I was going to grow, so I added the zinc pretty quickly. But you can also add it at a very slow rate, perhaps over a day or 2 days, and you might be able to see something like larger single crystal growth, which can be useful for some things. But in my case, I was just looking for a uniform powder. So as long as throughout my synthesis, I was able to maintain the same rate of addition, I was hoping to look to create a uniform powder there. I also used a mortar and pestle to grind up the MOF5 after I had synthesized it to hopefully be able to have an even more consistent powder. So at this point, I was able to complete that synthesis, and hopefully I was able to build the apartments. And now it was moving on to checking the specifications. So to check the specifications, the main tool that I used was X-ray diffraction. And X-ray diffraction is a very, very useful tool for examining solid state samples in particular. And it's important that we measure MOF5 in the solid state, because if the MOF is not in the solid state, well, then you really have ceased to have a MOF at all. Because they are these particularly set up frameworks, they always have to be in the solid state. And if you think you've gotten a MOF into a solution phase, well, then you've actually just lost the structure entirely. So X-ray diffraction is really, really useful for MOFs in particular. And on a pretty simple level, the way X-ray diffraction works is you have your X-ray source, you have your sample, and you have your detector. And notice that we are beaming X-rays from the source off of the plane of the sample into the detector. And notice that there's an angle of theta made between the source in the sample plane, as well as the detector in the sample plane. Now, this is important to note because when I actually show you XRD spectra, we're going to be looking at an x-axis of 2 theta. And the reason our x-axis is in 2 theta is because of the symmetry between the theta angles you see here. So as the X-ray source is increased in its theta value, the detector is also going to equally increase in theta value. So that's why we're going to end up with that axis condition. Now, on a microscopic level, what we're really looking at here is a lattice of our atoms. So if we imagine that these gray dots are atoms set up in this lattice construction, and then the red incoming arrows are our X-rays, what we're going to see is that we're looking at deflection off of various sublevels of our framework. So we see that some X-rays will bounce off of the top level, bouncing off of a gray dot. Some will be able to penetrate a little deeper and bounce off of a different atom. And actually, depending on how the path length, how you measure the path length difference of the X-rays after they've been reflected into the detector, we're actually able to get measurements out for different distances between different atoms in the framework. Now I can actually go ahead and show you some of my powder X-ray diffraction data of the MOF5 that I synthesized. So note again that we have 2 theta on the x-axis, and then on the y-axis we have intensity. I don't have any units here nor numbers. It's not particularly important what the absolute intensity value is here. What's more important is, for 1, peak location, and for 2, the relative peak heights between the different peaks in the framework. So I was able to get this spectra of my MOF5, and then I actually went ahead and compared it to some simulated spectra that I was able to find in the literature. So what we see here is that there are some discrepancies. For 1, there are 2 locations where my peaks don't match up with that of the simulated spectra, both at about the 5 and about the 11 2 theta mark. We're also going to see that my relative intensities aren't exactly right. I normalized the highest peak in both spectra to each other. That's the peak around 7 on the x-axis. We notice that the rest of the peaks in this simulated spectra don't really match up with the synthesized. Now, this might seem like a pretty large issue, but what I actually found after diving deeper into the literature is that there are some different things about MOF5 that don't necessarily make it a super consistent for characterization. What I've actually found is that based on how you choose to synthesize MOF5, and throughout the literature, people have synthesized it in a variety of different ways, you end up getting different things. There are actually 2 substructures that make up the MOF5 structure itself. So what we end up seeing is that we have these substructures, and they might appear in different relative amounts depending on the way that you synthesize your MOF5. So you're going to end up with different relative peak intensities and also slightly different peak locations. Now, that makes me think that it's okay to keep going with my project, even though this spectra doesn't perfectly match up. And in addition to that, as long as I have a framework that I'm pretty confident has MOF5-like characteristics, as long as it's consistent throughout my project, it should probably be good enough for developing this type of method that I'm interested in. Obviously, I'm not trying to 100% characterize something new here. The goal is more this method development. So as long as my MOF5 is consistent, it should be good enough for what I'm looking to do with it. So at this point, I was able to check my specifications. Obviously, there might be some doors on some ceilings, but we'll leave that for someone else. I have hopefully what I would call my MOF5, and now I can move on to opening the apartments. So what I'm going to be looking for here is we're going to be looking at what actually makes up an EPR active molecule. So the most important thing that makes a molecule EPR active is that it's in a non-zero spin state. And the easiest way to get a non-zero spin state is by having an unpaired electron. So in both of these structures that you see down below, you see a small black dot on one of the atoms, and that denotes that there is a single electron there. And the reason that that single electron gives us a non-zero spin state is because electrons come in either spin up or spin down orientations, also denoted as spin plus 1/2 and spin minus 1/2. And normally, electrons really like to be paired up. So whenever you see electrons in bonds, we're looking at two electrons that have been paired up, both an upspin and a downspin, so their net spin becomes 0. When you have a single electron, we're actually looking at a non-zero spin state because it's no longer paired up in that way. And well, these species are actually already pretty exotic. It's kind of hard to find them in general. What makes it even, what was another barrier to entry for finding a molecule that I could use for my project here was finding a molecule that was also persistent. So because these electrons really like to be paired up, they're extremely reactive, and very quickly most react with the atmosphere or other things around them on a very, very quickly, way too quickly for any type of process that I was hoping to do with them. So instead, I had to look at the specific class of persistent radical molecules. So triphenylmethyl and tempo are both examples of these. And there's a couple different ways that this stabilization of a radical can occur. So for one, in the case of triphenylmethyl, we have that electron denoted on the center carbon, but that electron can actually resonate throughout those outer benzene rings, and that will add some amount of stability there. And in the case of both of these molecules, what I think is an even bigger deal is there is steric hindrance to attack upon the place where the single electron is. And so what I mean by that is in the case of the triphenylmethyl, those benzene rings are actually slightly rotated as marked by the bold black line. And so those are rotated, and those R groups are actually able to block attack from the top and bottom of the molecule. So the whole goal here with steric hindrance is not allowing any type of molecule that would want to attack the electron or the electron would want to attack the other molecule to really even get close to that place. In the case of tempo, while the electron is denoted on the oxygen here, most of the electron density is actually nearer to the nitrogen or in a bonding orbital between the nitrogen and the oxygen. And so there is actually a fair amount of steric hindrance with just those CH3 methyl groups that are able to block attack on that electron. So the molecule that I ended up choosing for the study actually was tempo for a couple different reasons. For one, just like I talked about how MOF5 has been well documented and around for a while, tempo is a persistent radical that has been around for many years, I believe since the mid-1900s. So it's a very, very well-known persistent radical. It is quite persistent. It will not necessarily just dissipate into thin air. It's not going to react very quickly with the atmosphere around it or in many different conditions. So I thought it would be a good candidate for using in this type of quantitative study. Another benefit is that, at least in theory, it would fit inside of the pores of MOF5. It would be able to fit through the holes. So at this point, I was actually able to move to opening my apartments. I was able to submerge MOF5 in a solution of tempo and DMF. The goal here was then, of course, incorporating the tempo into the framework. So then I would remove MOF5 after certain amounts of time from the soak to hopefully be able to start developing the type of data that I was interested in looking at. So up next, I was actually moving on to taking a census of the population, and here's where the EPR instrument really comes into play. So on a base level, the way that EPR, or electron paramagnetic resonance, again, works is using magnetic fields and microwaves to interact with those non-zero spin states, as I talked about a little bit earlier. So in this picture, you can see an example of what you might see coming out of an EPR. You would normally get your spectra out in a first derivative curve, as is noted here. And for those of you who are more used to an absorbance curve, you can actually just take an integral of the first derivative, and you're going to end up with something that looks a little bit more like what you'd get out of a lot of other instruments. But most people who work with EPR work with the first derivative curve, and that's just because that's the way the data is actually collected by the instrument. So on the x-axis, you'll see magnetic field strength, and then on the y-axis, you'll see nothing here. In most cases, you'll just see intensity. It doesn't actually have a unit there, and it's not particularly useful, except for in the case of this quantitative data collection that I'm interested in, or if you want to compare two different spectra to each other, you could, look at the differences between their intensity. So the reason that we have magnetic field strength on the x-axis is because I would do a type of EPR called continuous wave EPR. And this is a very common type of EPR to do. And the way that continuous wave EPR works is that while continuously beaming the sample with a particular power of microwave, we vary the magnetic field strength from low to high, and it generates this first derivative curve. Now, the reason that it generates this curve is due to something called the Zeeman effect. So, in absence of a magnetic field, when there is no magnetic field, the spins of the electrons, both up and down, will be at the same energy level. But as we start to apply a magnetic field, we begin to start seeing what's called the Zeeman effect, where the energy level between the upspin and the downspin starts to break apart. One moves to be lower in energy and one moves to be higher in energy. And so we can actually then access this very, very small change in energy with a microwave. So we can use a microwave to perturb the low energy spin into the high energy state, and then we can also watch it relax. And that's kind of the basis of how EPR works, is by splitting the energy level of these spins. Of course, we have these single electrons that we're able to perturb, and then we can use that to create our spectra that we're interested in. So as I've already talked about, EPR can be used very well to do quantitative analysis, provided parameters are set correctly and the data is very carefully taken. This type of technique that I was planning on using here was actually something I had used previously a couple of summers ago in some research that I was doing with a different metal organic framework. In this case, the guess that was being taken into the framework was not itself a radical, but rather it radicalized the framework around it. And then based on different amounts of guess doping, we were able to get different sample curves. You see sample A, sample B, sample C, based on different amounts of doping. And from here, quantitative data was able to be collected. Now, normally to get quantitative data out, or like your number of spins that you actually have in the system out, it's a very, very large equation. But luckily, most of modern computer software is able to do most of the equation for you. So there's only a couple key things that you have to be careful about. Now, using this type of technique, it would be potentially possible to look at different curves, like your time versus your spin count curve, and be able to analyze things like, okay, what's the general shape of the curve we're looking at? Maybe it's logarithmic, maybe it's linear, maybe it's something else entirely. This type of technique could also be used with different solvent conditions. So in the case of MOF5, it's already known that DMF is much harder to remove from the pores of MOF5 than chloroform is. Normally, if you want to use MOF5 for something, you will soak your MOF5 that you synthesized in DMF in chloroform for a while to be able to remove all the DMF from the pores. But if we were able to see other aspects of guessed inclusion, maybe using this technique, we could maybe see that the DMF would be something like the red curve, whereas the chloroform would be something like the blue curve, where chloroform is more easy to remove by the guest, thus giving us a higher spin count earlier on. So as you can see, I've been talking about those last two things a little bit more theoretically, and that's because I actually wasn't able to really get to that point in the project. I ran into a couple different issues and some other just interesting things that would happen when I was incorporating the EPR active molecule into the framework. And so I'm going to be talking to you guys about that now. But what I would like to point out is that I still do have confidence in this project in general. I think that at its base and at its core, it can still definitely work. And I think that the work I've done up to this point can definitely be expanded on to be able to make this method a reality. So before I really get into talking about my spectra, what you're going to notice is that all of my spectra with tempo has 3 EPR peaks. And the reason that this is due to hyperfine splitting and coupling to the nitrogen atom spin. So we have our electron atom spin, and now we have the nitrogen atom spin. And remember, I said a lot of the electron density in tempo is actually on the nitrogen. So if we look at this image, we see we have our Zeeman term, which is the term that I was talking about earlier with our single electron. We have our negative 1/2 spin and our positive 1/2 spin that are being split in energy by our magnetic field, and that would give us our single peak. Now, if we introduce our nitrogen actually has 3 different spin orientations, either -1, 0, or 1. And what we see here is that each of these three states splits each of the two states for the electron into three states. So we end up getting 6 total states here. And so you might be wondering, well, why don't we see, a lot more peaks than just 3? Maybe because there's so many different possible transitions between all of these different energy levels. Well, the reason for that is because of selection rules. So each of the transitions that are allowed in this system have to follow a very particular set of rules. Those rules being the spin of the nitrogen cannot change, and the spin of the electron must change by 1 or -1. So as we can see, there end up only being 3 allowed transitions between the 3 different nitrogen spin sublevels. So now we can move on to actually looking at some real data that I collected. This is just tempo in a dichloromethane solution. This is just kind of a basic picture of what a tempo spectrum might look like. So as we'll see, we have the magnetic field on the x-axis. And again, we have intensity on the y-axis that's unitless. And notice about this spectra that we have our 3 peaks. Notice that they're all pretty symmetrical, which is really nice. And also notice that they're not infinitely sharp peaks. In theory, we might be thinking, okay, well, maybe they can be infinitely sharp, but that's not really true. There are a variety of different factors that influence peak broadening. In some cases, those types of factors were actually affecting some of the data I was collecting, though that shouldn't necessarily have an impact on the quantitative aspect of this data collection. Normally, as much as the peaks broaden, they also get shorter, and that's actually proportional. So the integration should be about the same. And the integration is what's really important for the quantitative data collection. Another thing that is important, though, is if the line with broadening gets too big, the peaks might start to overlap. And if the peaks start to overlap, that actually would begin to cause a problem for quantitative data collection. Now, another thing that was causing maybe some problem with the quantitative data collection, but is actually pretty interesting to think about, is something called anisotropy. So as we can see in this spectra below, that middle peak is still pretty sharp and pretty normal looking, but the 2 peaks on the sides are quite different. They have a very, very different character to them. And that's caused by this thing called anisotropy, which isn't necessarily something that we can just inherently remove. It's just a natural part of the system, but it does make quantitative data collection perhaps a little bit more difficult. And so this anisotropy is actually caused by the tempo having the characteristics of being in a solid state, which is really, really interesting because that would mean that if tempo is being incorporated into the framework, its movement is actually being restricted in a way where it wouldn't be able to freely rotate as much as it would be in the solution phase. And that's pretty cool. So to get a little bit more in depth on anisotropy, we can come to a simple example first. So we can think about trying to measure the diameter of a sphere. And in this isotropic system case, that's what we would be doing. If we had a sphere, we were measuring its diameter through the center from any possible frame of reference, we'd always end up getting the same value, which is called it would be an isotropic system in that case. But instead, if we look at our anisotropic system, where we have a cylinder, if we measure this cylinder from a variety of different axes, we'd get a bunch of different measures for the different directions that we're measuring through it. And so that would give us our anisotropic system. Anisotropy can actually be averaged out, though, if that cylinder were to be, let's say, spinning freely in solution. If it spins quite quickly and we're able to take adequate data, it would all end up averaging out to give us our isotropic system. So if we actually think about the example of tempo in this case, again, here is the tempo molecule. Notice that we have our single electron. In this case, it's denoted between the nitrogen and oxygen, which is pretty fair. We have a variety of different measurements depending on the axis of measurement of the molecule. So if we were to take EPR in the X or Y frames of reference given here, we'd see that our spectra are pretty similar. There's obviously a little bit of a shift in the spectra, but overall, the difference between the peaks is relatively the same. But if we compare that to the Z-axis spectra, we'll notice that the difference between the peaks is much, much greater. There's a lot more space between those peaks, and that can start to cause some issues of anisotropy. Another thing that was causing me some amount of issue was microwave power. So if we look at this curve here, we see we have microwave power on the x-axis in milliwatts, and we have peak-to-peak amplitude on the y-axis. So peak-to-peak amplitude is the difference between the highest point on the first derivative curve and the lowest point on the first derivative curve. And as you can see, there is a curve there But really what we want to be seeing is some type of linear region, probably right around near 0 microwave power. You might notice there's some places that look a little bit linear in the higher microwave power regions, but those are actually just due to the way the data was collected in this case. But we would be really hoping to see a linear region closer to 0. And normally when you do quantitative analysis, you want to be measuring within that linear region where the relationship between the power and the amplitude is linear, because it can start to cause problems if you're working outside of that region with the quantitative analysis. So to kind of bring it all back to what this project was really trying to focus on, what we were really trying to look at, well, for one big thing that we were hoping to get to is looking at the effect of different solvents on the uptake of guests into this framework. Again, trying to see how we could see different spin counts based on how quickly different guests were incorporated based on different solvents within the pores. We were also hoping to look at just have a more general idea of the time scale for how long it takes for uptake. We would be hoping to see, okay, well, does it take hours? Does it take minutes? Does it take days? We would guess somewhere around the hours region, but we weren't 100% sure. We might also want to be wondering different questions about equilibrium and things like that. But again, this project ran into a couple different road bumps kind of in more of just the EPR collection aspect. So for one, we were looking at the issue of microwave power. And one potential fix I could see for this microwave power discrepancy is probably by lowering the concentration of tempo that I was using for my soaks. EPR is actually a very sensitive technique that can work down onto the 1 micromolar scale of things in solution. And I was working at, I would say, 10 to 100 times larger than that. So I think that could definitely affect something called, it could definitely affect this curve here. In the case of the anisotropy, I think this is more of an interesting avenue to pursue, though it does inhibit the quantitative data collection. But anisotropy is actually quite a well-documented phenomena, so I wouldn't be surprised if there was a way to incorporate it into the quantitative aspects of this project. All right, I want to thank you all for listening. In particular, I'd like to thank the Lawrence University Chemistry Department. You guys have all been so awesome and supportive for the last 4 years that I've been here. I've learned so much and really developed as a scientist in a way that I really, really appreciate and enjoy. I'd also like to thank Graham Sazama in particular, because he has really given me a lot of tools to use in my own research. He's been such a great research advisor and really been able to help direct me in the way that I want to go and where I want to take my science. I'd also like to thank Daniel Martin and the whole stockroom. The stockroom is just always there to be able to help with all the things that I would ever need. I myself have been a stockroom employee for the better part of my 4 years at Lawrence. And I'd particularly like to thank Daniel because he is just always someone who I'm able to ask all of the little questions that I don't really think about early on in a project and generally get some very, very valuable answers. I'd also like to thank all of my peers. It has been such a wonderful 4 years working with all of you. We've all done so much. We've gone through so many different classes, and it's just been a really, really wonderful being able to learn with you all. All right, thanks again, and I'll take any questions.
Let's clap, yay! All right, Evan, your youngest student was here for the whole talk. She gets her hair from her mother. Do we have questions for Evan? I'm sorry, Iris, I didn't understand that question. Oh, go ahead, Camille.
Hi. Nice talk, by the way. Oh,
thank you.
Cool. Yes. My thing was just, so you mainly characterized your MOF5 through powder X-ray diffraction, right?
Mm-hmm.
Did you do anything else to characterize it? Or like, why was the PXRD just like sufficient enough?
So I actually did do something else called BET, or like pore size analysis. So I did use another technique of characterization. I didn't really talk about it. That gave for a couple different variables, different for some measures of surface area and for pore volume. It gave consistent results with the paper that I was looking at. But for another type of surface analysis, it gave rather inconsistent results. But that is also something that I had seen across a variety of different literature. There was a lot of discrepancy about what that value was. So It was mainly powder X-ray diffraction and then this BET characterization.
Other questions? Feel free to unmute yourself and ask away. No more questions for Evan. It was a clear talk.
So this is someone named Oriel who is not related to Evan. Best kid name with Iris, but I just wanted to thank you so much for, well, hi, there's another human.
The whole gang is here. Yeah, that's Sam.
Sam, hey. No, but just gratitude for really amazing mentorship, which it's a huge deal. And I'm just a random, not chemist logging in. Thank you.
Evan practically mentored himself, so it was a pleasure. Okay, well, if there are no further questions, I will lead the round of applause. Thanks again, Evan. And remember, everybody, tomorrow at 11:10, we'll have Vivian Polkenhorn, and we're looking forward to that talk as well. So hope to see you all there. And great job, Evan. Thanks a lot.